Okay, so there has been some mention of restraints, and there are quite a few different restraints that come into play. Pavel described some of them. This talk is going to generate, is going to concentrate a little bit more on the chemical restraints and covalently bound restraints, but it doesn't exclude the others. So this is going to talk a lot about ligands, because those are in your models. And why are they in your models? Well, it's often because you have inherited it from the model that you downloaded or got from some other source. And they can also, the models can also contain water molecules. So when you inherit a model, there's pluses and minuses. One of the minuses is that it might contain something that is not in your model. And you have to be able to see them in the map if you're going to produce a reasonable model, of course. So by see them, you can look at them in the density and see whether they actually are there. And here's two examples. I got these from Christopher. He's in our group, and you can see on the left the ATP at just worse than 4 angstroms. It appears to be there. It has a CC mask of 0.5. Whereas the instance on the right, the ATP is not in any density at all, and the CC mask is -2.7, and the resolution is 7. So one of the minuses of using inherited maps is that sometimes the ligands just are not seen in your data. So ligands in action, and when you have a ligand, and it also goes for the standard proteins and RNA, DNA bases, there's libraries that are distributed with Phenix, and some of the restraints that we inherited came from the monomer library, and we've also developed a library called the GeoStandard, which has a lot more detailed information and some annotations to make the restraints better for your modeling. And this also contains lots of rotamer information as well, and updated restraints for your protein and nucleic acids. But there's also algorithms in Phenix that will provide things like polymerization. So if you think about it, each one of the amino acids in your protein is in fact is basically a unit which has some restraints, but it also needs to be linked to the next unit in the protein chain or the nucleic acid chain. And this polymerization is done with a combination of code and restraint files. And then other links like metal coordination, links between ligands and protein, for instance, those links which are not polymerization are also done in a similar fashion, and sometimes more programmatically than previously. So the GeoStandard contains all of the amino acids. It also contains the non-standard amino acids. Each time that gets updated by the RCSB, that is updated. Also contains all of the standard nucleic acids, and the non-standard nucleic acids are being added systematically. It also contains a lot of other things, important ones, and other entities that have come to light, and I've added those with some validation as well. an important thing that is very common in cryo models is that you often don't know the sequence, or you can't register the sequence because you don't know exactly where the sequence is in the map. So commonly the UNK entry is used. This is a cut down, if you want protein amino acid, that is often put in there if you don't know what is actually the amino acid in place. But you should know that it is actually, this is what it actually is. It has these atoms and these atoms only. You can have less, of course, but you can't add other other atoms to it. So as a small side note, it should be noted that CIF stands for crystallographic information file. And there is an CIF, which is macromolecular CIF, and it's becoming more and more used for all sorts of information. So you can have your model in CIF format, you can have your data in CIF format, and that at the moment is mostly for X-ray people, but that doesn't preclude the cryo, because maps can also be stored in CIF format. And then for ligands, there's two types of CIF files. There's one that's informational, and it can be downloaded from the PDB in either it's called the ligand depot or the chemical components. This is information about each of the ligands, and actually all entities in the that have been deposited in the PDB. And you can also have restraints in CIF format, and these restraints is what I'm going to talk about mostly today. But that does cause some confusion. As of July last year, all X-ray models have to be deposited using the CIF format. This may be coming soon. It may not be coming as soon as some people think for cryo, but it's definitely coming. And when you say you need a CIF file, you should actually be a little bit more specific now, because before it used to mean I need a restraints file, and that's what we should be saying now. So restraints. What are restraints? They're used to provide reasonable geometry for a refinement during low resolution. And in this particular case, I'm talking about bonds and angles, dihedrals, chirals, and planes. These are chemical and chemical type restraints, and they are commonly called internal coordinates. So, and they form a large part of the refinement because they're weighted against the experimental information. So if the resolution is better, then the restraints are down-weighted. If the resolution is poor, the chemical restraints are up-weighted to give you a reasonable model. So the three tools that are commonly used is ELBO, which is short for a ligand builder, which creates restraints, and it's quite a diverse and multi-usable tool. Ready Set is a way of getting just about everything that you need in the large proportion of cases to start your refinement. It will add hydrogens, it will create restraints for you. And Real is an editor which you can use to create better restraints, and you'll even change them if you are knowledgeable. So ligands in refinement, you need to generate the restraints. You also need to fit the ligand to the density. This is the ideal way to go about your task if you know you have a ligand and then you are adding it. If you inherit a model, as I said before, you should check that the density supports the ligand, and then you can refine your macromolecule annually. The goals of ELBO were to make the creation of restraints much more simple. Prior to automation, that often were done by hand, editing a file and everything. So this tool removes the tedium. ELBO does create chemical restraints for an entity, and it does create Cartesian coordinates as well, specifically in the PDB format, but other formats as well. And those will be passed on to your refinement program so that you can provide as much information as you can. So this diagram is perhaps a little bit more information than is needed, but it serves to point out that with ELBO, you need to create some sort of internal topology. Now, I said earlier that if you inherit a model from somewhere and it has ligands in it, that you have to be careful. But one of the pluses of that is that if you inherit and take the model from the PDB, then the three-letter code for each of the entities in that model are known. And that at the top right there is what I'm calling the three-letter code. That three-letter code can be used directly in ELBO to create restraints if it's unknown. So what happens is that you will try to run real space refine. It will pop up and say you don't have all the restraints you need. You can choose to run ready set, or you can choose to run ELBO with the three-letter code. The use of the three-letter code is a very much simplified and a much more robust way of getting restraints. So if you wish and you want to, you can go that way instead of using ready set, because at super low resolution, ready set will add hydrogens by default, and that may not be what you want to do in all cases. So this is just telling you that after the topology of the ligand has been created, it can do several different ways of getting a good geometry, and then it outputs these files. I should point out that if you're working on novel ligands that in the drug setting where you're working on creating drug targets, etc., this is not quite as common in cryo-EM, but it's not uncommon. Some pharmaceuticals are doing drug design studies using cryo, so this may actually come into play at some point. So, as I said, you can instead of doing it by hand, you can use ready set. Ready set, as I said, adds hydrogens, and it uses reduce, which is a program written by the group of my next speaker, and uses ELBO to create restraints and add hydrogens to the ligands, and it does a few other things of which are not super important to you at this point. So in real space refine, one of the things that is a little bit unusual in Phenix in general, but also in real space refine, is that link records, which is part of the PDB input, are not used. They are ignored. So we don't trust any link records that are being input into the Phenix programs. So if you wish to make some links, the standard residues are automatically linked so that they polymerize, as I hinted at earlier. There is a parameter that's link all equals true, which will, based on proximity and based on atom type, we'll try to generate links for ligands to be covalently bound to the protein. Carbohydrates, if modeled appropriately, will be linked, and the appropriate link will be applied. If you have carbohydrates, you'll know that they're quite complicated and that there's something in the order of 200 different types of carbohydrates, and there's something like a dozen different links between them, types of links based on chirality and atom naming and everything. There are a few nuances that need to be removed to make this a little bit easier for people, but I'm working on that. Also, metal ions can be a problem. Some ions have different coordination, and sometimes you need to create links between metal ions and their surrounding automatically, which is done by Phenix refinement when it's loaded. Sometimes you have to create manual files. These two situations, the carbohydrate and the metal ions, are still require some intervention on occasion, and those are the types of examples that you should send to me, and I can try and help you out with some of the details. The same goes for nucleic acids. They are linked automatically, and you can also create secondary structure restraints for them by either in the GUI, asking the GUI to do that, or you can do it at the command line. And then what then happens is you have the files, all the information to create hydrogen bonding between the base pairs. You can also create restraints that will try and keep two base pairs either in parallel across the base pairing, or also in the stacking, and that's known as parallelity. That was mentioned earlier, I believe, and it can be done using secondary structure restraints for that situation. I also mentioned NCS restraints, but these have all been mentioned. The custom bonds and angles, this can be done using edits, which is available in the documentation, but there is a slightly fancier way of doing it, which is called SIF links, I'm sorry. And if you want to use SIF links, that's also in the documentation, but it does have a slightly different mindset. So if you want to hear a discussion about that, I can have that offline. One thing that everybody should be aware of is that when you run a real space refine, every restraint is written into a file called the .geo file. And if you look at that file, it's very large, but it does have every bond that is added. It has every angle, every plane, and every planarity. So if, for instance, you have an edits file and then it doesn't seem to be doing what you want, this is the place to look to see if you have, in fact, succeeded in your quest to create a link between two entities. Now, it is quite large, like I said, but it's also ordered in groups of type of restraint. So bonds are first, and then edited bonds are after that are in some groupings. And it also shows you the worst offenders for variance from the mean. So the first bond that you will see is the one that is the most stressed, or has the biggest sigma outlier. So that is definitely a place to look if you're having issues. Now, I hope that I have given you the main points of restraints, elbow and ready set will perform better if you have better input. And that is true of just about every program, garbage in, garbage out. And you need to know something about your ligand and your model. In the last talk, it was stated that you should look at your model in the map to see what's going on. This is true with the case of ligands. One nice feature in Coot is that there's a button at the top which takes you from one ligand to the next, and you can click on that and it'll loop through all the ligands, and you can look at it and you can say, yes, this ligand seems to be correct, this ligand does not. And I recommend that you do that. Also, as I stated earlier, check your geo file for confirmation of your restraints. Thank you.
So, questions for Nigel. There's been some in the chat window. I'll mention a couple here. Trying to find this. So somebody asked, and just so you can maybe say a bit more about this, that will elbow generate coordinates for a new ligand that you just have a smile string for?
Yes, and I sort of didn't mention that except in passing. The elbow does do that. Elbow is designed to create restraints for novel ligands from a large number of inputs. And I have slides for that as well, but I did not show them. The thing is that means you have to know a little bit more about your ligand, and you have to have some idea of how to validate it and have reasonable expectations. So one of the cool things about elbow is that it will interface with Mogul, which is a very nice validation package from the Cambridge database people, the small molecule database, and most of you can probably access that for free. It's very easy to get it from most universities and educational institutions. If you install that, elbow will generate very, very nice restraints for you. There's also the other thing for elbow is that not all of the three-letter codes are shipped, restraints are shipped with Phenix. So you do have to use it occasionally to create those three-letter restraints. So yeah, if you have Mogul there as well, you can either use it to create the restraints, or you can use Mogul to validate them. I see another question from Bonnie. Best practices workflow when working with metals. Let me answer that. There's not a good tutorial anywhere. I'm sorry, that is on the list to generate it. At the moment, the metal coordination stuff is in a state of flux. If you'd asked me this question a year ago, I would have said that there's different features available in Phenix. So first thing I would do is run it without the metal restraints and see what happens to your metal center. Because Phenix will try to do something for you automatically. That there is a sub option in Phenix Real Space Refine. It says you can turn on and off link metals. You should take a look and see what happens. If the link metals is not working for you, or it's either linking incorrectly or linking too long and too short and things like that, then you need to go the edits route, which is the file that's created by ready set. So at this point, best practice, run it, see what happens. If it makes a mess, please try and quantify what's going wrong, and then we can help you with that. Okay.
There was a question earlier on. I just want to make sure we got to, which was little bit related, which was, I was from Bonnie as well, actually. So when automatically creating links to metal ions, is there a good tool in Coot to ensure that the starting model we use has a correct distance between the metal and the side chains?
No, I do not know of one. He's just released a new version, which seems to have a lot of features. And besides, the tools in Phenix have an idea of what is a good default distance, which is another thing to keep an eye on. It takes default distances from different literature that I've read and added to the file. So hopefully it's quite accurate, but Phenix doesn't rely on the input geometry to create the default bond length. If that answers your question, I see another question about three-letter code ligands in Coot doesn't have the same as in Phenix. That is probably because some of the restraints in Phenix are the old version, the version 2 version that is on my agenda to get rid of all of that. Your choice is depends which way you want to do it, but either Coot or Phenix will take the restraints from the other program and use it almost seamlessly. You just have to provide one or the other with the other program's restraints library. And I can certainly help you with that. Whichever three-letter code you're talking about, I can expedite the change for you.
So a question from Robert, is there a good way to refine nucleotides manually in a structure it's hard to rotate around angles in Coot?
That might be more a question for Pavel or Oleg. I haven't tried to rotate a base of a nucleic acid. So.
Well, yep, I think that's probably a reference to the backbone. So we don't have any manual model manipulation tools in Phenix, so we do rely on Coot. And yeah, as Nigel said, there is a new version and maybe there's improvements, but I know that historically nucleic acids have been harder to deal with. There is a
comment.
Jane?
We do have oh, sorry.
Feedback.
Yeah. Okay, we were having feedback problems between our two computers. Sorry. But there is an option in Phenix to link to eraser. If you really want to fix nucleic RNA backbone, that's the way to go. But it requires setting up Phenix and Molprobity and Rosetta, which is not simple, but it's incredibly effective. And we've spent years trying to edit nucleic acids by hand, and I don't recommend it.
Yes, no, that's a very good point, Jane. There is the eraser tool that in theory does automated rebuilding of nucleic acids. I have to say at the moment it doesn't work because of that code has not been maintained by the Stanford group, so it doesn't currently work. Yeah. We've encouraged them to try to fix it so it does work, but right now I don't think it's available in the GUI. But yes, it would be great to get that working because eraser is a powerful tool.
Yeah, they're actually using it inside some of their other packages, so they have to have it working, but it's not compatible with some of the other things. Like it's not currently at all easy to set up separately, unfortunately, because it really does work.
Yes, I know. So yeah, it's unfortunate because it's when it's set up and working, it actually is very powerful. So we can hope that they fix that because that would be. I think it would help, Robert. It would help actually the eraser tools. Another question: what is the best way to covalently make an S linkage between a peptide and a lipid molecule?
So it depends on the situation. So I alluded to it in my talk, but there are three ways to make a linkage. If it automatically links because the covalent bonding, the ligand covalent linking has been turned on and it creates a link, then that might be satisfactory for you. If you wish to be more hands-on and create the link yourself and not rely on the automation, the two methods are edits or SIF link. Now, edits are sort of a one-shot thing. You create them and that works for that situation. If you want to reuse the information, so for instance, you have 5 lipids in this model and 2 in another, and you know that they're S-linked to different peptides, you might want to create a SIF link file, which you then apply to those entities just by putting in a couple of lines in another file. That is a great way of specifying bonds, angles, and other types of things that you can reuse. So it really depends on that situation. Now, I would be very interested to see the model that you're speaking of, because I can probably help you quickly, and I might even add it to Phenix as an automatic feature. So please, I don't know how to say your username, but please send me the model if you